All right, so we're almost to the end of Chem 1315. We're going to talk a little bit about functional groups of organic molecules. Those functional groups determine how an organic molecule reacts in general. And so functional groups are classified, organic groups are classified according to their functional groups. Now, functional groups are a specific series, a specific way to bond things to the organic compound. And the functional groups are determined determine its physical and chemical properties. Functional groups affect the polarity of a compound. All right, so therefore, the way the functional group works or what it is makes a difference in the organic intermolecular forces. Just a minute, I want to resize that. So we can see it all. So the type of functional group is very, very important to the intermolecular forces. Functional groups have high regions of electron density and low regions of electron density, and that makes a difference on how reactive they are. And so in your book, there's a table. This one I've made it in half so we could see it a little better. First thing on the list of the type of functional group is the alkene with the double bond, and we've looked at these already. Okay, so that's the first type of functional group, and also the alkyne with a triple bond is a functional group. We're going to look at some haloalkanes. Typically, those are going to be a long chain with an alkane on it and some kind of halogen, like a chloride or a bromide attached to it. And so we'll look at a little bit. I got a couple of examples for you on those. They're named almost the same as you would name anything in the alkanes that you looked at, except you would include that instead of being just a methane, it, in this case, has a chlorine molecule on it, atom, so it would be a chloromethane. We're going to spend quite a bit of time thinking about alcohols. We're going to spend a lot of time thinking about alcohols, and I'll go on to that in a minute. We'll look over amines and all of the rest of these functional groups. For the most part, as we proceed through this lecture, you should know what these functional groups are. I expect you to be able to pick them out off of a molecule and correctly identify different types of functional groups. So I wanted to talk about haloalkanes for a minute. So I just wanted to show you, for example, if I was asked to draw 2-chlorobutane, I would start with my long chain. In this case, that's 4 carbons because it's butane. And I'm told there's a chlorine atom on this molecule. Then I would go through and I would add all of the proper hydrogens, and it would look like this, and I would write it as CH3, CHCl, CH2, CH3. What if I wanted to know about 2-chloro-2-methylpentane? In fact, let me draw it and let's see if you can see where I've tricked you. That's not, that's right. Well, no, that's not even right. 1, 2, 3, 4, 5. I want 5 carbons. I guess I won't trick you. Never mind. All right, so I'm told it's 2-chloro, 2-methyl. 2-chloro, 2-methyl butane. Pentane. I'll get it straight. Pentane. I've drawn my 5 carbon chain, and I'm told there's a chlorine here and a methyl here, and then I would fill in the rest of these hydrogens and then translate that into my condensed formula. I'm sorry. Okay, next one is alcohols. Now, alcohols are a very important group, and we're going to spend a lot of time looking at some of the reactions they do. An alcohol functional group has an organic chain. Remember, R stands for any chain, bonded to some OH group. Now, I want you to be very, very careful here, because this is not a hydroxide. It's a functional group off of the organics that is an alcohol. This indicates an alcohol. It does not indicate a hydroxide. And when you name alcohols, which I don't really expect you to be able to do, but when you do, you change their name from the E in the parent hydrocarbon to the ol. So, for example, if this is just a one-carbon alcohol, this would be a meth. Remember, methanol. Okay, methanol. That indicates it's a hydrocarbon with one OH group, indicating an alcohol. And methanol, by the way, is very, very dangerous to you personally, so be careful about methanol. Alcohols have high melting and boiling points because they can undergo hydrogen bonding. Remember, when you have a nitrogen, an oxygen, or a fluorine actually bonded to hydrogen, that allows you to undergo intermolecular forces, polarity, and hydrogen bonding. And you should probably be able to connect this with your Unit 7 material. So let's talk about a few alcohols. For example, we just did methanol. We can have longer chains of alcohols, so we could have a CH3, CH2, CH2OH. We would call this 1-butanol. All right, now, even though at the end of the chain, I would start numbering 1, 2, 3, because the functional group typically gets the highest numbering. Or I might ask you something like, no, I'm not going to ask you, but let's look at it. Something like isopropyl alcohol, isopropanol, propanol, with the OL at the end. And in this case, the OH group is bonded to the second carbon here. And I can add out the ends of this, and I'll need a hydrogen here, isopropanol. And so let's look at the hydrogen bonding for a minute. We'll take the simple methanol molecule, and I'm indicating the OH group. Now, the oxygen, this is going to be partially negative because the oxygen is pulling some of the electrons away from, electrons from other things. And then in the next molecule over, this might be attracted to the hydrogen at the OH because this is partially negative and this is partially positive. Okay, and then so the next group over might have the hydrogen attached or bonded, hydrogen bonded to another similar molecule here where there's an interaction between the positive charge, partially positive charge on the hydrogen and the partially negative charge on the oxygen. And so these things would have very strong intermolecular forces because they can undertake hydrogen bonding. And they're also polar. Okay, now one thing I do expect you to be able to do is to be able to identify types of alcohols. So there's going to be three types that we need to deal with. The first one is called a primary or a first-degree alcohol. And the way we make these decisions is we pay attention to the carbon that the alcohol group is bonded to. And the question is, how many carbons is the carbon with the OH group bonded to? So we don't care. We're not looking at the OH or the alcohol group. We're looking at the carbon it's bonded to. Now, in this case, this carbon is bonded to only one other carbon, and that's called a primary carbon. Okay, so it's just bonded to one other. Here's a secondary carbon alcohol, though. In this case, the OH is bonded to a carbon that's bonded to this carbon and bonded to this carbon, and so that's a secondary alcohol. And then on a tertiary alcohol, a third-degree alcohol, you'll notice that this carbon bonded to the OH group is bonded to this carbon, and this carbon. Remember, it can't be bonded to the hydrogen in between because hydrogen only has one bond. So this is indicating that we have the H, C. We'll leave that CH3 like it is, and CH3 here. But anyway, the idea is all the hydrogens on these are, remember, bonded to, oops, oh, that's okay, I can do this. Still, even though it's turned, it's still got the same structure here. Anyway, so this is called a tertiary alcohol or a third-degree alcohol. And in that case, it's bonded to three other carbons. Secondary are bonded to two other carbons, and primary is bonded to one other carbon. And I told you that I don't really expect you to name the alcohols, but do remember you replace the E, for example, instead of having methane, you would have methanol. And we're going to see alcohols undergo. We're going to do some oxidation reactions here. They can also undergo substitution and elimination, but we're going to concentrate on oxidation and the formation of ester, which we looked at, or we didn't look at, but I put into the simple organic reactions that you should be able to identify. All right, so let's draw up some structures here, and I actually don't want to do these. I think I must have, I guess I didn't. I thought I'd put in a page because I wanted to concentrate on what the primary, secondary, and tertiary possibilities could be. So if I draw ethanol like so, this carbon is bonded to one other carbon, so this is a primary or a first-degree carbon. Now, would it, just as a point of matter, would it make any difference if I made the reaction run, the alcohol look in this direction? And the answer is no, because no matter whether I have a 1 or a 2, I would end up numbering this. I would end up numbering this 1 and 2 because either way, the alcohol gets the first number. What about something like 2-butanol? 2-butanol. Well, in this case, I've got a 4-carbon chain, and I'm told that my alcohol group is at this carbon 2. number these just to be good. And so when I add in the hydrogens to make this fully saturated, I end up with a structure that looks like this. Or it might be written CH3, CHOH, CH2, CH3. What kind of alcohol group is this? Well, we're focusing on the carbon that the hydroxide is attached to. So this carbon, and in this case, that's bonded to this carbon and this carbon, so this is a secondary alcohol. How about 2-methylbutanol? So in this case, again, we have a 4-carbon chain. We're told, I'll tell you what, why don't you name this? Okay, well, we know that the chain is a butane, but it's got this this OH group on it, so we'll call it butanol. And then we need to number it, and so in this case, we'll have a 2-methyl, oops, I may not have left enough room, 2-butanol. 2-methyl-2-butanol. In considering what kind of alcohol this is, we're going to look at the carbon bonded to the OH. That's bonded to this carbon, and that carbon, so that's a tertiary alcohol. Now, the reason I want you to care about that is because I want you to look at some oxidation reactions for alcohol. Now, oxidation in electrochemistry means loss of electrons. And that is what oxidation means, loss of electrons. But when you're dealing with organic, you can usually just say loss of hydrogens. Okay, so in an oxidation of alcohol, I'm going from some alcohol on a primary chain to something called an aldehyde. It's just, this particular one's called an aldehyde, formaldehyde, but that's an aldehyde where I have a carbon double bonded to an oxygen, and then the 2 hydrogen atoms to make carbon have follow the Lewis dot structure. In this case, this would be an sp2 hybrid orbital, and we'd call this 120 degrees, right? Here's ethanol. Again, the the alcohol group is at the end, and so it's another primary. And in this case, we get acetaldehyde. In that case, notice that this is going to look like this, where I have a double bonded carbon and oxygen, and then I have to fill out the rest to make that carbon, this carbon, follow the Lewis dot rules. So let's talk about that aldehyde that it formed, that we were just looking at. This is called a carbonyl group, and several organic structures have carbonyl groups. And that means the carbon is double bonded to an oxygen. So the aldehyde here is at the end of a chain. I want to make that clear. Notice this is some chain. It can be a 4-carbon chain, a 25-carbon chain, whatever it is. The aldehyde is at the end, this group, COH, with some chain attached to it. This group is always at the end of a chain. The aldehyde group always at the end of the chain. So here's our acetaldehyde or an ethanol. Whoops. Well, I guess I thought I had a slide in here, but for secondary alcohols, the oxidation gives a ketone. Now remember, secondary alcohol, let's use butane again. 1, 2, 3, 4. We'll put the OH group here. Okay, so that's our secondary alcohol because this carbon is attached to 2 carbons. Now this ketone has another carbonyl group. In this case, we have some chain and another chain, or some part of a chain, any kind of hydrocarbon chain, but in the middle of that chain somewhere, doesn't have to be right in the middle, but somewhere not at the end, you get a carbonyl group that's just a C double bonded O. So, for example, if we were using our 2-butanol here, we'd have CH3, CO, CH2, CH3, after it undergoes an oxidation. And this is, like, for example, R, C, I'll put my O down here so I don't leave myself any room, to another part of the chain, so some R prime, ketone. That is a carbonyl group in the middle of the chain, or somewhere not at the end. Carbonyl group not at the end of a chain. As it turns out, tertiary or third degree carbon alcohols do not undergo oxidation. Now, another carbonyl group that I know you've heard of are carboxylic acids. And carboxylic acids are at the end of a chain. Okay, so here's some chain here, right here. And at the end of the chain, you get a molecule that looks often written like this. So in this case, we have the carbonyl C double O and then an OH, not an alcohol, but an OH. It turns out, and this is why they're called acids, that this hydrogen can be easily ionized, and that makes it an acidic hydrogen. So that's why we call them carboxylic acids. You'll also see them written like this in the condensed form, where you should know right away that there is this kind of a structure on it. All right, so you should be familiar with both of those. I want you to notice carboxylic acids are at the end of a chain. Just like when we had aldehydes and ketones, both of those are C double bonded O's. The aldehyde is at the end and the ketone is in the middle somewhere. Carboxylic acids are at the end. They're a type of group. Now, I can take an alcohol and some kind of an acid, and I can make another carbonyl group called an ester. All right, so in this case, I have some alcohol, and I have some acid. And I see my double bonds kind of got moved over. Oh, and here too. This should be to the carbon. Now, in this case, I've got an ester, and an ester has the formula R, some chain, with the carbonyl and this oxygen and some more chain. All right, so what I end up doing when I'm doing a condensation reaction where I split out water, I end up, well, I don't really care if you know what the mechanism is, but I end up getting this kind of a structure. And then, in this case, split out water. And esters smell pretty good. For example, you can make things that smell like bananas. Okay. Okay, I hate it when I say okay, I'm sorry. And so here is the ester group. Notice that it's a little bit different from the carboxylic acid. This is in the middle of a chain somewhere. It doesn't have the hydrogen on it because I only use the hydrogen to make everything obey the octet rule. But in this case, since the oxygen's bonding onto something else, it doesn't have a hydrogen. Anyway, and so you'll see these are kind of named funny. For example, this is the methyl, and then here is, oops, that's not the methyl. The methyl group is down here, and here is the 2-carbon ethyl type of group, only in this case it's not ethyl because the functional group is this ester, but it's still 2 carbons long, so it's called methyl ethanoate. I don't care if you know how to name these. I don't really expect that. I expect you to be able to figure out what the functional groups are here. Now here's amines. Amines are some bond between carbon and nitrogen. Some bond between carbon and nitrogen. So, and they're also classified like alcohols, which we're not really going to look at, but if it's only bonded to 1 carbon, it's primary. If it's bonded to 2 carbons, it's secondary, and if it was bonded to 3 carbons, it would also be tertiaries. These are going to be singly bonded between the carbon and the nitrogen. And then the nitrogen, nitrogen will have however many hydrogens it takes, and whatever it takes to follow the Lewis rules. In this case, there's a lone pair of electrons on there. In this case, let's do something like CH3NH3. Again, I have a hydrogen and 2 bonds to carbon, and then that lone pair of electrons gives me the valid Lewis structures. And they smell badly. Okay, so amines have lovely names, get to be really interesting, like cadaverine, or putrescine, But at any rate, whatever these are, for example, let's just look at this very end here. This would be an NH, lone pair of electrons bonded to this long chain of carbons. All right, so amines are bonded to a carbon, a nitrogen bonded to a carbon, and however many hydrogens and lone pairs of electrons it takes to make the nitrogen follow the octet rule. Another type of functional group that you should be familiar with are the ethers. Ethers are used as anesthesia and things like that. They smell relatively good, but they're kind of dangerous for you. And let's notice that we have some chain, and in the middle of it is just an oxygen. It's not a carbonyl group. It's just got the oxygen. So, for example, this is called dimethyl because in this case it has a methyl group on each side and then ether. This one is diethyl. It has an ethyl group on each side, and then you call it an ether, so you know that this is going to be a bond that looks like this. This is the dimethyl ether. And now we'll have, remember the oxygen as what always follows the Lewis dot structure rules, the octet rule, never an exception in this class: carbon, nitrogen, oxygen, and fluorine. Amides. Amides are very important. You'll find them in polypeptides, in our proteins, and so forth. And in this case, we have a carbonyl group, the double bonded carbon-oxygen group, and the nitrogen group. Okay, so in this case, you've got a C double bonded O, N, and H. It could be something else, but it's usually going to be an H. That's called amide linkage, and that's what forms your proteins, and many other things for that matter. Amides are involved in all kinds of plastics and other polymer formations. Let me see. Well, I guess that's pretty much what I'm going to say. Now, this is a simpler, if you know how to read it, this is a little bit simpler little table about your functional groups. So, of course, the alkenes and the alkynes are still on here. It just doesn't happen to be on this list. But hydrocarbons have some kind of halogen bonded to it, like a bromine or an iodine or a chlorine, whatever. Alcohols have an OH group, not a hydroxide, but an alcohol group bonded to a chain. Ethers have just the oxygen bonded to two chains. Aldehydes have a chain with the carbonyl group at the end of the chain, has to be at the end. Ketones are similar, but they're in the middle of the chain somewhere. So they're not at the end. They're very much like aldehydes in their structure, but they're not at the end. Acids, again, those are at the end of some chain, while the esters are in the middle of some chain. In the middle. And then there's the amines, where the amine is bonded to a CN, or the amine is a CN, and the hydrogen will have however much it takes to make it fit through the octet rule. I'm sorry. And then there's the amide. It's not on here, but the amide is a carbonyl type group, and in your proteins and in your D and so forth, that's called a polypeptide or a peptide bond. Now I want to talk briefly about polymers. Polymers are organic chains of carbon, and you tie those units together. So let's look where this M represents some unit molecule. It could be more than one. It's more than one atom. It's some kind of a unit, and we call that monomer. There's just one of them. When there's two units of whatever attached together, they're dimers. 3 units are trimers. And many, many, many units are polymers. And so there's all kinds of polymers, by the way. I mean, besides the industrially produced things like plastics and so forth, I mean, there's silk and proteins and polypeptides and so forth. So I want you to focus on 2 types of polymers. There's condensation and addition polymers. Addition polymers undergo, shockingly, an addition reaction, and they usually contain an alkene group. They usually consist initially of some kind of an alkene group. And condensation polymers have 2 different functional groups. There's two two different things with two different functional groups, and by dehydrating the reaction, you can link those two different monomers together. So here's a simple monomer for addition. In this case, notice that this is the ethene. Ethylene is the common name. Under IUPAC, you'd call that ethene. It has two carbons and a double bond between them. And you could do some kind of a reaction that will breaks the double bond, and the next carbon comes in here and attaches. And so you end up having many, I only showed two full ones, but you can have many units of this singly bonded now CH2CH2 unit. Now, I put this in here not because I want you to know it. I do think radicals are interesting because radicals, remember, are those structures we drew in our Lewis structure work where we had just one electron, some odd number electron on an atom. And that's called a radical. They're very, very reactive, and they will do whatever it takes to get themselves back into a state of octetness. But that means that because they've reacted to get their extra electron, then the next thing also becomes something that's got an odd number, and it starts a chain reaction. Okay, so a chain reaction ends up giving you these long polymers under an addition reaction if you start with a radical. Now, the reason I actually put this on here, though, is when you get to organic chemistry, you'll learn something called mechanisms, where, for example, if we have this ethene group and another ethene group, you learn how the electrons move, and you show it with something called a mechanism. So in this case, what happens is this gets attached here, this gets moved there, and so you have to look and see how all the electrons get moved around and why, and you have to understand intermolecular forces and types of behavior of the different kinds of atoms. So I don't really expect you to understand any of this. I want you to know, though, and this is actually really cool stuff, mechanisms. If you can follow the electrons, you can figure out what's going to happen to various types of substances. Now, the other kind of polymer I want you to be aware of are something called condensation polymers. In this case, remember, we have two different units. So here's unit 1, and here's unit 2. And so these can be forced or interacted in some direction so that the two monomers end up linking together. So in this case, we're going to lose this OH group here, and we're going to lose this hydrogen right here, and we're going to form this molecule where, I wish this was a little closer together, but where this piece of that monomer is now bonded to this green thing. And water, the H and OH, comes off of here. And I also want you to see, just in this case, I started with some alcohol. It happens to have two, some kind of a di-alcohol, has two alcohol groups on it. And I have some kind of an acid. And when I form this turns out to be an ester. If we were drawing this, we'd put in O, C, O, and then our next polymer unit. Okay, so it just happens to be an ester in that case. And since it did, I thought I'd keep it so I could show you that one more time. Okay, that's the end.